Good day, I'm Norman Wildberger. There are serious problems with the current theory of real numbers, and we are trying to lay out what these are in various contexts. We've already had a look at real numbers as infinite decimals and the various problems associated with that point of view. Today we're going to look at another way of approaching real numbers, which is through the idea of a Cauchy sequence of rational numbers. This is one of a number of different ways. There's also the approach of Dedekind cuts. There's also an approach of continued fractions. There's another way of approaching real numbers through axiomatics. We're going to try to show that none of these really work. They all have serious logical difficulties. Today we're going to start looking at this issue here, which is a very big topic because it involves concepts which we haven't talked about before in this course on foundational mathematics. So it's going to be necessary for me to introduce various ideas from modern analysis in order to be able to critique this particular approach to real numbers. It's probably fair to say that this is the definition of choice for most analysts. A real number is an equivalence class of Cauchy sequences of rational numbers. So in today's lecture, we're going to start moving towards understanding what this means. We're going to have an initial look at sequences, limits, Cauchy sequences, rather in an informal way to begin with, to give you a sense of what these things mean. And we're going to need to take care that we don't assume that we know what these words mean already. Okay? Each of these words is going to have to be looked at very closely and carefully. With the definition of sequences, the various problems are very parallel to problems with functions. So you might like to have another look at Math Foundations 42 to remind yourself of some of those difficulties. We are tackling the idea of trying to describe the continuum, a line, starting with the rational number line and then trying to see whether we can augment that to get real numbers. The discussion is a little bit hard to visualize sometimes because of the small nature of the line, the fact that it's rather constricted. It turns out that a lot of the ideas can be more easily explained in a two-dimensional setting rather than in a one-dimensional setting, which is a bit ironic because the two-dimensional setting is perhaps more complicated. But we can at least visualize things and some things become clearer. So I'm going to try to give you some introductory ideas in the planar context. We're going to look at sequences of points in the plane. And here are a couple of different sequences illustrating different things that sequences can do. Here's a sequence of points, S1, S2, S3, S4, S5, S6, S7, and they seem to be marching roughly in that direction at more or less a uniform pace. Here's another sequence, U1, U2, U3, U4, U5, U6, U7, which is also going in that direction and seems to be getting closer and closer to the S sequence. So these two sequences are getting closer and closer together as we carry on. We might say that the two sequences are converging towards each other. This is not, in fact, such a standard terminology in pure mathematics, but it is very common English usage of the term. When two paths come together, we say they converge. Here's another sequence, the T's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and perhaps carrying on. This sequence seems to be spiraling around, and it looks like there's some kind of movement towards a final point, which is perhaps somewhere in here. So this looks like a sequence that maybe has a limit. Here's a sequence, R1, R2, R3, R4, R5, R6, R7, R8, that just goes around and around these 4 points. There's clearly no limit. There is certainly a very clear pattern, just going around and around and around. And here is a very simple sequence. V1, V2, V3, V4. It's a constant sequence where every point is exactly the same one. So you think of just a bunch of blipping points always in the same spot. Well, here you have blipping points moving around. So these are examples of different kinds of behavior of sequences that can happen in the plane. Of course, there could also be a very random kind of sequence, a sequence which just hops around rather randomly. That's also possible. But we're going to be thinking more in terms of sequences which converge either to another sequence like this, or perhaps converging to what looks like some kind of limiting point. So this main idea for a definition of real numbers that we're trying to understand is this one here. That a real number is, by definition, an equivalence class of Cauchy sequences of rational numbers. So we'd like to understand what that means, or at least what mathematicians would like it to mean. It's rather a complicated story, as it turns out. It's rather a sophisticated notion. There's a lot of different ingredients there, and a lot of them are problematic, require quite a lot of preparation. So both the notion of an equivalence class and the notion of a Cauchy sequence of rational numbers have to be understood. So to try to get some initial sense of what this means, I'm going to stick with a two-dimensional story, and I'm going to give you a two-dimensional analog. Let's consider over here the situation where we have a particular point, the point 1, 1 in the plane. It's got a rational coordinates 1, 1, right there it is. Now we can imagine sequences that move towards that point. For example, here's a sequence of blue points which is moving steadily towards that red point. Here's a sequence of black points moving towards it. And here's a sequence of green ones, a little bit more erratic, still eventually moving towards the red point. So each of these three sequences is moving towards or converging to this point. In fact, they're also converging to each other. As they move closer to this point, they are also getting closer to each other at the same time. That's an important observation. So here we have actually three converging sequences. Three sequences, they're all getting closer to each other, and they also happen to be getting closer and closer to this rational point 1, 1. Now let's look at a situation over here where we know there is no rational point. Let's look at the circle, x squared plus y squared equals 1, and the line y equals x. And we've talked already about where these two meet. The line and the circle, in fact, don't meet. There is no rational point where they meet, even though it certainly looks like they do. In order for a point to exist, it would have to have the form 1 over root 2, 1 over root 2. And we've already talked about the problematic aspect of root 2. This is a fictitious kind of object. It doesn't really exist. There is no point where the line and the circle meet. Okay, but the analyst will say, all right, there may not be a point yet, but we can create such a point. We can construct such a point, sort of filling in the gap that seems to be obviously there. And here is the beginnings of this idea. What we do is we consider sequences that are moving towards this imaginary non-existent point. So here's a sequence of green points moving in the general direction of where the circle and the line seem to meet. Here's a sequence of blue ones. Here's a sequence of black ones. And all three sequences are converging to each other. They are getting closer and closer together to each other as they move in this direction. So there's no point that actually they are limiting to. It's quite different from this situation here. But nevertheless, we have these three sequences that are getting closer and closer together. So in both cases, all three sequences are converging. So the idea, and it's rather a very nice and elegant idea, is to say, all right, let's try to augment our plane by introducing a new point. And what this new point is going to be, well, it's going to be these sequences. The sequences themselves we're going to consider as a kind of an object. As long as the sequences have the property that they're getting closer and closer together in a certain way, like these ones are. So the idea is to replace the non-existent point there with this family of sequences which are moving toward what that imaginary point might be. It's an interesting idea. The question is, can we make it work or not? So let's have a look what it looks like sort of on paper, this idea. So the idea is we've got this fictitious point P there that we're trying to define. We're trying to bring it into existence. And the idea is that we're going to group all the sequences which converge together towards this mysterious non-existent point P. And we're going to define P as that set of converging together sequences. So for example, if this particular sequence is, say, the sequence S1, S2, S3, and this one here is T1, T2, T3, the blue ones, and the black ones are V1, V2, V3, and so on. And here's another one, U1, U2, U3, U4, the red ones coming together like this. All of these four sequences have the property that they're getting closer and closer together. They're converging to each other. And they also happen to be getting closer and closer to where we think this point ought to be. So the idea is we're going to define this point P to be the collection of such sequences. So it's going to be a set, and it's going to have various objects in it. The objects are themselves sequences. There's the S sequence, there's the U sequence, the T sequence, the V sequence, and then there will be a lot of other sequences too. Basically, any sequence that we can draw on the plane that eventually starts heading towards this region, or actually ends up heading towards exactly the same place that these sequences are heading towards, whatever that means. Okay, so this is a two-dimensional picture. A real number is going to be a one-dimensional version of this. We're going to do the same thing, or try to do the same thing, on a one-dimensional line. And it's a little bit harder to visualize because there's not so much room. Here, I think it's easier to see what the basic idea is. All right, so this is a very interesting idea. Can we define new numbers of this kind? Certainly you can see this is going to be a lot more complicated than with rational numbers. Okay, with a rational number, you just have a single rational number like 3 over 7. Or 1,249 over 3,478. The numbers can be big, but there's still only two of them, one on top of the other. Here, we have, well, it turns out an infinite number of sequences. And as we'll see shortly, in a few videos, the size of this infinity, whatever that means, is even larger than you might think it ought to be. And each of these elements in turn is itself an infinite sequence. So we have an infinite set of infinite sequences, and these sequences are all related in some way, that they somehow converge in the same general way to each other. It's a very complicated object. A single real number is going to be a major complicated thing. And you can see why in treatments of first-year calculus or even second or third-year analysis at the university level, people are reluctant to go into a lot of detail as to how this exactly works. It's going to be clear that at the very minimum it's going to be very complicated. A lot of work is going to have to be done. We're going to be challenged to set up a complete theory of arithmetic with the fundamental objects being so complicated. And I claim that it in fact doesn't work. Okay? That it's a mirage. That it's something that is good perhaps in principle, but when you actually look at the details don't stack up. The thing does not fit together in a proper mathematical format. That's my claim. We're going to look at this in much greater detail than is traditionally done almost anywhere else. So in the next few videos, we're going to have a very, very good look at this idea. You're going to learn real numbers probably better than you do in any other place. So with this initial orientation to what a real number might be, I think you can appreciate that there are going to be some serious challenges. At the very least, we are going to have to deal with these issues. We're going to have to understand what we mean by a proper definition of infinite sequence of rational numbers. It's clear enough what a finite sequence of rational numbers is. We are going to have a very clear understanding of what we mean by an infinite sequence of rational numbers. And when we look carefully at that, we're going to see that this fundamental divide between infinite choice and computable that played a major role in our discussion for infinite decimals is going to raise its head here also. We're going to need an appropriate notion of converging together sequences. What does it mean for two sequences to kind of be converging together in the way we want them to be, so that there's some kind of limiting point that we can create from the sequences? And that's not so easy, but the great French mathematician Cauchy outlined the basic idea there. So there's a notion of Cauchy sequences that we're going to have to understand. That's going to be the main tool to get on to that aspect of things. We're going to need a prior theory of infinite sets, because we're defining this real number as an infinite set of sequences. So we have to know what an infinite set is, whether we like it or not. We better have a theory of infinite sets. This is a major problematic business that cannot be avoided if you want to go down this route. Cannot be avoided. In fact, we're also going to have to consider not just so-called countable infinite sets, but also uncountable infinite sets. And you might as well know that as far as I'm concerned, there are no infinite sets at all, countable or uncountable. They're all just fairy tale objects. And then, of course, we're going to have to define an arithmetic with these objects. Once we've defined the real numbers, well, then we have to say how we're going to do the operations, and we're going to have to try to prove the laws of arithmetic. That turns out to be not as painful as you might think. There's some issues, but it's not overwhelmingly difficult. It turns out to be a little bit easier to define the arithmetic with these Cauchy sequences than it does with infinite decimals. So this is a trade-off that we get when we look at these different ways of approaching real numbers. In some of the methods, one kind of issue is more problematic, and in another method, another kind of issue is more problematic. But unfortunately, there's always something that's problematic in all of these approaches. I want to give you just a bit of an idea of what this Cauchy sequence idea is. It's a very critical aspect of this approach. And to make that a little bit easier, in today's lecture, we're just going to assume we already know what an infinite sequence is. We're just going to draw pictures and not be too precise. And we are going to work, as I've said, in the plane rather than the line, because it's easier to visualize. And the main thing that we need in the plane is the idea that if we have 2 points, we can measure how far apart they are. And the way we measure how far apart they are is not via a distance. Please, it's not a distance, it's via a quadrance. So at the point A1 with coordinates x1, y1, A2 with x2, y2, the quadrants is the sum of the square of the difference of the x coordinates plus the square of the difference of the y coordinates. There's no need for a square root. That's how we're going to measure the separation between 2 points. And if quadrants is a little bit unfamiliar to you, have a look at, say, the Math Foundation lecture number 25. Or you can look at the entire Wild Trig series, which is all about quadrants as a basic notion for doing geometry. So this comes down to two different approaches to the convergence of two sequences. Here are two different pictures. Here is a pair of sequences, and these sequences are converging. R1, S1, R2, S2, R3, S3. And as we're moving along, well, we're heading in that direction, but the quadrants between corresponding points is getting smaller and smaller as we move along. So we can say that the sequences S1, S2, S3, and R1, R2, R3 converge precisely when the quadrants between the kth element of S and the kth element of R goes to 0 as k increases. Admittedly, this is a little bit loose. We need to clarify exactly what this means, but I think you can have an intuitive understanding. As k gets bigger, in other words, as we're moving through the sequence, the quadrants between the corresponding elements gets smaller and smaller and smaller, closer and closer to 0. So that's a definition of what it means for two sequences to converge. That, however, is not the kind of convergence that's needed for the real number definition. For the real number definition, we need a tighter form of convergence, a more stringent form of convergence. This is the Cauchy notion of convergence. And let's illustrate it over here in this picture. So here we have a sequence S1, S2, S3, S4, S5, and as we're carrying on, the values of the sequence are slowing down, and they're getting closer and closer together to each other. They look like they might be approaching something, but we're not sure. Here's another sequence, R1, R2, R3, R4, R5, and so on, and it looks like they're also ultimately slowing down and moving towards something, perhaps. So these two sequences also converge in this sense. So if we looked at the quadrances between corresponding elements in the sequences, say S6 and R6, that separation, and then S7 and R7, S8, R8, we'd notice that those quadrances are also getting closer to 0. So these two sequences converge in this sense. But, and here is the important point, they converge in a stronger sense than just that. They converge in this Cauchy sense, which is that the quadrances between SK and RL go to 0 as K and L increase. In other words, it's not just pairing SK with RK where the indices are the same. We're comparing an arbitrary element in the S sequence with an arbitrary element in the R sequence. And as long as the indices are sufficiently big, then the 2 points are close. So here, for example, if K and L are both big, but not necessarily equal, for example, K could be 1,000 and L might be 3,000, then still if we look at S 1,000 wherever it is and R sub 3,000, those 2 points are going to be very close together. The quadrants between them is going to be close to 0. So this is the Cauchy notion of convergence. It doesn't apply over here. These two sequences do not converge in the Cauchy sense because, well, if they keep on doing like this, taking sort of equal steps like this, then we cannot expect, for example, S sub 1,000 and R sub 3,000 to be close to each other. They're not going to be close to each other. Yes, S 1,000 is going to be close to R 1,000, but it's not going to be close to R 1,001. Some dramatic difference between these two sequences and these two sequences. And so the analyst says when we want to define real numbers as equivalence classes of sequences, we've got to be working with this Cauchy notion of convergence. So that's a very important idea in modern analysis, in fact. Very important idea. Unfortunately, the reality is that trying to set up a theory of real numbers as equivalence classes of Cauchy sequences of rational numbers is very, very difficult, and it's fraught with logical complications. And in fact, it's rarely attempted in its entirety. So what happens is that students are told about this, and they might be told a few things about it, and maybe even a few things are proven. But in terms of having a systematic, complete layout of this theory, it's almost never done. It requires more than just a few days' effort. And when you look at it closely, as we'll see, well, the problems are quite significant. So something to keep in mind here with this discussion. It's very easy for us to get confused and very easy for us to start crossing over from mathematics into philosophy. I'm not really interested in philosophy in terms of mathematics. I would like to remove philosophy from mathematics. And I think one way of orienting ourselves in this direction is to concentrate on explicit examples and concrete computations. These are two things that can anchor us to reality. So if we have some complicated theory and we're not quite sure, do we understand this theory or not? We look for explicit examples. We try to make sure that the examples actually correspond to the definitions. So we match up the examples with the definitions. And we try to make concrete computations. We say, let's put this into practice and see what happens. So in our next video, we're going to move towards a more careful understanding of these various issues. And a good place to start is by looking at the structure of the rational numbers. The rational numbers are the framework in which we are working and trying to set up these real numbers. The rationals are much more complicated than people think. They have a very deep structure, in fact. And it's a very good idea to understand a little bit that deep structure of the rational numbers. So we're going to have an initial look at that next time. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.